Phoenix is a lander that's going to the North Polar Highlands of Mars to look for evidence of habitable zones, places where life might have existed in the past.
Moving flight hardware, not even to mention an entire spacecraft, is usually a delicate affair. It's very meticulously coordinated. There's, arranging a police escort at 3 in the morning on a Monday morning, and all the state and local authorities that need to know about something like that, and all the paperwork that's required to essentially close down a section of the highway for a period of time. There's a whole analysis process that goes along with making sure that the spacecraft on the back of a truck, on a flatbed trailer, in the box that it is in, isn't going to be exposed to any environment that it's not rated for. So we know how much force a pothole in the road will induce on the spacecraft. Just a little bit into the trip, we had kind of a light rain. And that's another thing that just makes you ill at ease with your spacecraft that you've had in the clean room up until that point in time.
We have to fly a spacecraft on a plane all the way from one side of the country to the other. And that is a scary thing.
And you kind of look at the box and you look at the aircraft and you wonder, is it going to fit in there? When they open those rear doors, there's this cavernous space inside. Even as big as it is, this box just barely fits inside of it. It was a really kind of manual brute force operation.
It looks just like we're loading a box onto a plane. Inside this box is such an enormous treasure. This is something that these hundreds and hundreds of people have worked on to make it all come together. We've got Air Force pilots, most trustworthy people. They are flying this spacecraft from Denver to Cape Canaveral. And we trust these pilots, but we still worry. We're tracking this spacecraft and this plane as it's flying across the country. And as Florida comes into view, we think, oh, we're okay, and we can relax. We can't be relieved because we have still a huge amount of work to do to get this spacecraft to the launch pad, assembled properly, all fueled up and ready to go to Mars. Phoenix is a lander that's going to the North Polar Highlands of Mars to look for evidence of habitable zones, places where life might have existed in the past.
We're going to be repeating a number of tests that we did back in Denver, both to fully check out the spacecraft after the shipment, as well as take on some minor updates to the software that we've been testing with overall. Once we get out into June, then we've got a month that we'll be installing the ordnance and explosives onto the spacecraft that it needs to both separate itself and deploy the parachute.
This phase of the mission is basically the final checkouts and closeouts of the vehicle in preparation to made it to the third stage and to transport it out to the pad and get it stacked on the rocket and of course get it launched.
The most challenging part is as you get closer and closer to the end, there's less and less room to recover if something doesn't go right. So, it's really just managing things and being on top of every little item, because there's a point there where you can't recover, and you don't want to get to that point.
The biggest challenge this week is actually not the launch window per se, because it's an early morning launch, but we are in our peak afternoon thunderstorm time of the year. So the biggest challenges are the propellant loading that has taken place on the pad over the last couple of days, and it's been canceled because of the thunderstorms.
We were supposed to load oxidizer and then fuel onto the second stage of the launch vehicle today, and they got through the oxidizer load, and then the prediction for weather this afternoon was not good, so they decided to stand down from loading fuel, which means they have to load fuel tomorrow. And because of that, we'll likely slip the spacecraft launch from what was planned to be Friday morning to Saturday morning.
We have 2 days of our launch window before the shuttle. We have to stand down for the shuttle launch. And so we're hoping that if we either get off in the first 2 days or the shuttle gets off on its first day, so that then we can start planning to launch right after the shuttle.
7, 6, 5, 4. Main engine start. 2, 1, 0. And liftoff of the Delta II rocket with Phoenix, a distant science outpost seeking clues of the evolution at the polar region of Mars.
Being on the program as long as I have, it's kind of like your kid going off to college. You're very excited, you're very happy, but also sad that your baby's basically going to go away, and you're not going to hear from it again for 8 or 9 months. There's a lot of joy, a lot of sadness, a lot of nervousness, but that's part of the job, and we all deal with it different ways.
The Mars Phoenix lander is headed for the north polar region of Mars, and its goal will be to search for habitable regions, places where life may have existed in the past.
The phase that we're in now is called cruise,
which sounds really easy and laid back, although it's actually a very busy time for the spacecraft teams.
We're busy making sure the systems of the spacecraft are working as they should.
The teams are busily preparing for the science that's going to occur after landing.
And the navigation team is getting ready to make sure that the spacecraft actually gets to its target on Mars.
It's very similar to the sport of archery. In archery, you have the archer who's standing some distance away from the target, and that person's job is to make sure that the arrow hits the target.
An archer will have to draw back the bow with a certain amount of force. Secondly, the archer has to make sure that he aims the arrow at a certain angle, and then that arrow actually has to traverse the correct amount of distance so that it hits the target. These 3 things have to come together just right.
With launching a spacecraft to Mars, it's a little different. The bow in this case is a 250-ton rocket.
Our arrow is the Phoenix spacecraft.
It has to travel over 420 million miles to its target.
That's 70 miles long by 15 miles wide.
This is like trying to shoot your arrow from Dodger Stadium and hitting home plate at Wrigley Field in Chicago.
So this seems almost like an impossible shot to take just in one single shot. So we actually make it a little more fair by having 6 opportunities to correct that trajectory along the way. Imagine if you could shoot an arrow, stop it in its path, check to make sure if it's on course for the target, and if not, be able to nudge it back to its target so that it's headed for the right place. Now, of course, our spacecraft is moving at about 60,000 miles per hour. It never stops. So the corrections have to be performed along the way while the spacecraft is still in motion.
Phoenix is the first Mars scout mission. It's the first mission that's going to try to land near the North Pole of Mars. And it's the first mission that's actually going to go try and reach out and touch water on the surface of another planet.
Where there tends to be water, at least on Earth, there tends to be life. And so it's potentially a place where life could have existed on the planet in the past.
Friction really starts to build up on the spacecraft, and we use the friction when it is flying through the atmosphere to our advantage to slow us down.
From this point, we're going to decelerate from 12,500 miles an hour down to 900 miles an hour.
The outside can get almost as hot as the surface of the sun.
The temperature of the heat shield to reach 2,600 degrees Fahrenheit.
But the inside doesn't get very hot. It probably gets about room temperature.
There is this window of opportunity within which we can deploy the parachute.
If you fire the chute too early, the parachute itself could fail. The fabric and the stitching just pull apart. And that would be bad.
In the first 15 seconds after we deploy the parachute, we'll decelerate from 900 miles an hour to a relatively slow 250 miles an hour. We no longer need the heat shield to protect us from the force of atmospheric entry. So we jettison the heat shield, exposing for the first time our lander to the atmosphere of Mars.
After the heat shield has been jettisoned and the legs are deployed, the next step is to have the radar system begin to detect how far Phoenix really is from the ground.
We've lost 99% of our entry velocity. So we're 99% of the way to where we want to be. But that last 1%, as it always seems to be, is the tricky part.
Now the spacecraft actually has to decide when it's going to get rid of its parachute.
We separate from the lander going 125 miles an hour at roughly a kilometer above the surface of Mars, 3,200 feet. That's like taking 2 Empire State Buildings and stacking them on top of one another.
That's when we separate from the back shell and we're now in free fall. It's a very scary moment. A lot has to happen in a very short amount of time.
So it's in a free fall, but it's also trying to use all of its actuators to make sure that it's in the right position to land.
And then it has to light up its engines, right itself, and then slowly slow itself down and touch down on the ground safely.
Earth and Mars are so far apart that it takes over 10 minutes for a signal from Mars to get to Earth. And EDL itself is all over in a matter of 7 minutes. So by the time we even hear from the lander that EDL has started, it'll already be over.
We have to build large amounts of autonomy into the spacecraft so that it can land itself safely.
EDL is this immense technically challenging problem. It's about getting a spacecraft that's hurtling through deep space and using all this bag of tricks to somehow figure out how to get it down to the surface of Mars at 0 miles an hour. It's this immensely exciting and challenging problem.
Atmospheric entry on my mark. 5, 4, 3, 2, 1, mark. Expected peak heating rate in 1 minute and 40 seconds. Standing by for a possible plasma blackout. Phoenix now 1 minute past the entry point. We still have a signal via Odyssey. At this point in time, Phoenix goes normally through peak heating. Phoenix now 2 minutes and 25 seconds past the entry point. We still have a signal via Odyssey. Standing by for reacquisition via direct to Earth. Stop of Odyssey canister data and switch to 32K in 10 seconds. Standing by for expected parachute deployment. Parachute deployment trigger detected. Heat shield trigger detected. Ground relative velocity 90 meters per second. Land leg deployment trigger detected. Ground relative velocity 60 meters per second. Standing by for altitude conversion. At this point in time, Phoenix would have normally reached altitude convergence. We're standing by for confirmation via telemetry. Radar reliable. Altitude 2,000 meters. Altitude convergence detected. Altitude 1,800 meters. 1,700 meters. 1,600 meters. Standing by for landed separation. Altitude 1,100 meters. Signal may drop out during landed separation. Altitude 1,000 meters. The separation detected. We have verified the signal. Gravity turn detected. Altitude 600 meters. 500 meters. 400 meters, 250 meters, 150 meters, 100 meters, 80 meters, 50 meters. Come on. Constant velocity phase detected. Altitude 40 meters, 30 meters, 27 meters, 20 meters, 50 meters. Standing by for touchdown. Touchdown signal detected. Landing its sequence initiated.
One of the most interesting things about Mars is that it's changed over time. What we see on Mars today is very different from what occurred in the distant past. And water is the real interesting thing that we're looking for, the history of water, how it's changed over time. One of the biggest challenges to studying habitability on Mars, which is the goal of the Curiosity rover mission, is to try to follow that signature of water. Where was the water? How long was it there? And where do we go to look for evidence of it? If we were somewhere like this, where there's a pretty obvious just like this outcrop behind me, they give a record of time, of how things change over time. By studying different layers, you can rebuild the geologic history of Mars. So there's a place called Gale Crater, which has a 3-mile stack of layered rocks. Now, we don't exactly know how those layers formed, and the mineralogical evidence isn't as strong as other sites, but people who just think layers are the thing to study really love Gale. So you have these 4 different sites and these 4 different groups and very passionate arguments back and forth to try to really narrow in on what is the one site to send the Curiosity rover.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.